everyone. So in this video lesson, we will be talking about gravitation, not just for objects on Earth's surface, but expanding that out to talk about general universal ideas of gravitation between any two objects. Let's dive in. So some basic ideas of gravitation, just to review. First of all objects exert gravitational forces upon each other. It's not just gigantic objects like suns and planets and whatnot. All things exert gravitational forces on each other. You exert gravitational forces on all the other objects around you and vice versa. So this is true for anything that has mass, really. The strength of that force, though, depends on two things. Number one, the mass of the objects. Because you are super duper tiny compared to the Earth, you don't really notice the gravitational forces of other objects around you because the gravitational force of the Earth is so much bigger. So mass is one determinant of the strength of that gravitational force, and the distance between the two objects is the other. The closer objects are to each other, the stronger that gravitational force is going to be. So as a little reminder then, if you are looking for ways to increase your attractiveness, Newton says all you really have to do is get more massive and be a creeper and like stand really close to people. So Earth, we know, exerts this gravitational force on us, but as we've talked about before, unlike a lot of other forces like friction or applied force or tension force, gravitational force can act at a distance without actually touching us. How is gravitation able to do that? And the reason is because gravitational forces act through these things called fields. All right. Now, a field is a region of space, this sort of area around a person or a planet or an object, whatever, where we have this gravitational potential energy stored up, and therefore these gravitational forces can be exerted at a distance through this field, through this region of space. Now, we can't really see fields, but we can visualize them kind of the same way that we're able to sort of visually represent forces. We can't see forces, but we can draw arrows to indicate the direction that a force will act on an object. Similarly, we can visually, pictorially model fields by drawing arrows that indicate the direction that this field will exert forces on objects in various locations throughout the field. Okay, so let's go through and do a quick example of that, drawing the gravitational field of the Earth. Now, I don't know about you, but I've never had Earth like reject me and push me away. Earth loves me, Earth loves you, and therefore we know that this gravitational force, it's always attractive, it's never repulsive. So we know that the force acting on an object around Earth is always going to be pulling it in towards the Earth, towards whatever the source of our gravitational field is. So if you had, for example, an object at this location right here above the Earth, which way would Earth's gravity pull on the object? Pull the object downward towards itself because Earth loves us, okay? If instead there were something located underneath the Earth right there, which way would the gravitational force be exerted upon that object? Still towards the Earth. Earth loves the things at the South Pole just as much as the things at the North Pole. So it gets pulled upward, and if we have an object over here to the right, yep, it gets pulled to the left, all right? And blah, 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 blah. No matter where an object is in that gravitational field, the field and the force will always point inward towards the source of the field, always towards the Earth. So what that means is if we wanted to more fully and more thoroughly represent this, we might draw our gravitational field for Earth something like this, just a whole bunch of arrows pointing radially inward toward the Earth. That's our representation of our field because it tells us what the force from that field would be at a variety of different locations around the Earth. Okay. Now, another thing to note about this, to kind of tie it back to previous discussions about energy, we know that objects located in a gravitational field have gravitational potential energy. There's this energy that's stored up because they're located in the field in that way. Now, here on Earth, objects drop from high gravitational potential energy down to low gravitational potential energy. And it's really the same even as we extend the field farther and farther away from the Earth, okay? So if we have an object in this gravitational field and we just let it go and do its thing, it's naturally going to move from an area of high gravitational potential, far away from the Earth, towards an area of lower gravitational potential energy, closer to the Earth. And we know from previous discussions that ultimately that gravitational potential energy gets converted into kinetic energy, because as the object gets closer to Earth, that gravitational force gets stronger and stronger, and therefore the object is going to accelerate and it's going to gain speed, and therefore it's going to gain kinetic energy. So just a thought on that as well. All right. So then we've established that gravitational force depends on the mass of our objects and the distance between our objects. So gravitational force and mass have a linear relationship, okay? So if we were to increase the mass of an object, what would that mean for the gravitational force? Would it go up or down or stay the same? It's going to go up. So if we increase mass, we're going to increase gravitational force. Greater mass, greater weight, and both of those things change by the same factor. So if we double the mass of an object, we're going to double the gravitational force that that object experiences. Triple the mass, triple the force, etc. What about gravitational force and distance? What type of relationship relates those two together? Well, as we saw in our investigation in class, gravitational force and distance have an inverse square relationship, which first of all means that as we increase the distance between two objects, the gravitational force decreases. But it doesn't just decrease at like a 1-to-1 ratio. The gravitational force decreases really, really quickly at a faster rate than the distance increases by. So if we double the distance, the gravitational force drops by a factor of 4, not just a factor of 2. All right, and if we triple the distance, and the gravitational force drops by a factor of 3 squared, or 9. All right, so we see this very dramatic drop-off in gravitational force as we increase the distance between two objects. All right. So then this brings us to our universal law of gravitation. Now we know then that gravitational force has a linear relationship with mass, and so we see mass showing up in this equation in the numerator, not being squared, just a nice linear relationship. And we've got two objects in any gravitational interaction, and both of their masses make a difference. And so we see both masses showing up in the numerator of that equation. Now again, gravitational force has an inverse square relationship with distance, and therefore we see the distance between our two objects showing up in the denominator of this equation and being squared. Now if you just do the two masses multiplied by each other and then divide by the distance between them squared, that doesn't actually end up giving us the force inherently. We still have one more constant that we need to multiply everything by, which we call the constant of universal gravitation, or in other words, big G. Not little g, acceleration due to gravity on Earth. This is big G, this constant for gravitation that is true everywhere in the universe for all objects. We see this constant of 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. And that just shows up always in all gravitational interactions. We have to multiply that in there, and then we end up with our force in newtons, and everything is lovely. Cool. So here's one thing that's a little bit strange. We already had an equation for gravitational force. We had Fg equals mg, and now I'm throwing another equation at you. And this might feel a little bit weird. Like, why are there two different gravitational forces? Or are there two different gravitational forces? And the answer is there's not two different gravitational forces. Gravity is just gravity. That's it. Any two objects that have mass that are interacting with each other will experience these gravitational forces. That first equation that we've used previously, Fg equals mg, is really just a simplification that we use for objects that are located on Earth's surface. So let me show you how that ends up working out. Right? So imagine that we didn't have Fg equals mg. We only have Newton's universal law of gravitation, and we wanted to figure out what the weight of an object here on Earth is, what that gravitational force is. Well, we'd want to plug things into this universal law of gravitation, this gravitational constant times mass of first object times the mass of the second object divided by the distance between them squared. So if we think about an object on Earth's surface and the gravitational force between them, our two objects are the Earth and the object. So those are our two masses that are going in there. And then the distance between the Earth and the person is really just equal to the radius of the Earth, right? Even if a person jumps up a little bit or whatever, approximately the distance between the person and the center of mass of the Earth is about equal to the radius of the Earth. Okay, so we plug in all those values into Newton's universal law of gravitation. Now, for all objects, the gravitational constant stays the same. The mass of Earth still stays the same, and the radius of Earth still stays the same. Okay, so what I'm going to do is rearrange this equation a little bit, pull the mass of the object out, because that's really the one thing that changes for different objects located here on Earth. So then that gravitational force is equal to the mass of the object times g times the mass of the Earth divided by the radius of the Earth squared. Well, we happen to know those numbers, so let's just go plug those in. So if we took this gravitational constant, 6.67 times 10 to the negative 11, we multiply by the mass of the Earth, which is 5.98 times 10 to the 24th kilograms, and then we divide by the radius of the Earth squared. The radius of the Earth is 6.38 times 10 to the 6th meters. We plug that all into our calculator, let it do the computing. Guess what we end up with? What do you know? That big number turns into 9.8. Where have we seen 9.8 before? Oh my gosh, it is the acceleration due to gravity here on Earth. So that's really all that first equation is. It's the same as this new equation, just a simplified version so that you don't have to keep plugging in the mass of the Earth and other constants and all of these other things. Cute, right? Yeah. All right. Last thing, a quick sample problem for you. We've got a 90 kilogram person standing 1.5 meters away from a 60 kilogram person who's sitting on a bench nearby. We want to figure out how attracted to each other are they? Are they being like pulled towards each other? Like what is going to happen? All right. So here's what I know. I've got these two people. One has a mass of 90 kilograms. The other has a mass of 60 kilograms. The distance between them is 1.5 meters. And the constant of gravitation is the same everywhere and always. The 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. Then we want to calculate this gravitational force. So we plug all those things into the law of universal gravitation. Boom, boom, boom. All right. We plug all of those things in. Parentheses are going to be really important this unit, just as an FYI. And when we do that, do we get a big number, a super strong force? Nah, it's teeny, 1.6 times 10 to the negative 7 newtons, which is why you don't feel yourself constantly like falling into other people. At least I assume you probably don't normally do that. So anyway, that's why we don't really notice these gravitational forces from other people around us. They're there, but they're pretty darn small, and we don't really detect them. Anyway, that is it. Thank you for listening.